In section 7.7, we start looking at a characteristic of solutions known as the concentration. So this is a quantitative section of your book, so it's important to recognize that we're going to be doing math here, and as you're making notes on this content, I'd urge you to include as many as feels appropriate example calculations. So an important characteristic of a solution is its concentration, and the concentration is basically the amount of solute per unit of solution. And here we have two solutions. They both contain the solute hydrogen peroxide, and the solvent is water. Both of them have that solvent and solute, but you can see they have radically different concentrations. One is more than 10 times concentrated than the other. It has a lot more solute per unit of solution. And as a result, they have really different properties, right? One can be used as mouthwash or to clean wounds. The other you wouldn't want to have anywhere near your skin. It's going to cause painful blistering. In chemistry, the most common way that we express concentration is in terms of what we call the molarity, which is the moles of solute per liter of the solution. And this is indicated with either an uppercase M as the unit label, or moles per liter as the unit label. So the molarity has a really simple little formula. Molarity is just equal to the moles of solute divided by the volume of solution expressed in liters. And of course we can remember that 1 milliliter is just 10 to the minus 3 liters. Okay, so a very common problem is to be given the mass of a solute, the volume of solution that you want to prepare, and to be asked to calculate the molarity. So we need two things to calculate the molarity. We need the moles of solute and we need the volume of solution. Now in this case we've got the volume, but the amount of solute is expressed in terms of grams. So we need to convert that guy to moles. So how I'm going to convert this to moles is by multiplying by 1 on the molar mass. So the number of moles, and I normally use the symbol N to indicate the number of moles, is equal to 0.5 grams multiplied by 1 on the molar mass. And in this case, our molar mass, we've got 1 sodium and 1 chlorine. Our units of grams cancel out, leaving us with moles, and we have 8.5 by 10 to the minus 3 moles. What are we going to do with that 8.5 by 10 to the minus 3 moles? We're going to make it up to half a liter of solution. So in order to get the molarity, we take our number of moles and divide it by the volume of our solution in liters, which we were conveniently given. So now we can just go ahead and do that calculation. So it is 8.5 by 10 to the minus 3 moles divided by 0.5 liters. And here's our answer. And we're giving that to two significant figures because both of our starting numbers had two significant figures. So that's a pretty straightforward kind of calculation. Another type of calculation that you'll be doing regarding molarity is to calculate the mass of solute that you need to prepare a particular solution. So this one is asking you what mass of sodium chloride will you need to make a given volume of a solution with a particular concentration. And this problem looks kind of complicated to begin with, but we want to keep in mind our two formulas that we've got. So our molarity is equal to our number of moles divided by our volume. So that's just number of moles divided by the volume. We can reorganize this so that the number of moles is just equal to the molarity times the volume. Now our number of moles is also equal to our mass in grams divided by our molar mass, which I've indicated here. The number of moles is equal to our mass in grams divided by our molar mass, right? That's the mass in grams. And this is our molar mass. So what I'm going to do is I'm just going to kind of like squish these two formulas together, right? We've got two formulas for the number of moles. I'm going to put them both together, which is what I've done here. Okay, one of those two things are equal to each other. And now what you can see is that I can reorganize and get an expression for the mass in grams of my solute. So the mass in grams of my solute, here's our little formula, is just equal to the molarity of the solution that I'm making, the volume of the solution that I'm making, multiplied by the molar mass of my solute. So this is a super easy thing to answer. The mass of solute required to prepare a solution is just equal to the molarity of the solution times by the volume of the solution times by the molar mass of the solute. So this is the only formula that you need. Molarity times volume times molar mass will give you the mass of the solute. So it's straightforward. You're just going to multiply three numbers together. If you put your units in, everything should cancel out and you'll know you're on the right track. So our molarity, 0.5 moles per 1 liter. Our volume, so we got that. Our volume was 100 milliliters, which is the same as 0.1 liters. So that's what we got there. We got the volume. And then the molar mass of our solute, well, it's sodium chloride, so we've got the mass of a sodium plus the mass of a chlorine. And now when I go through and cancel out my units, liters cancels, moles cancels, and it just leaves behind grams. So how would I make this guy? 2.9 grams of sodium chloride would be diluted until I had 100 mils of solution. So this is a really simple problem to solve, just using this little formula here where you multiply the three numbers together. So those are the two most common calculations that you'll be doing involving molarity. In some applications, molarity isn't the best thing to be using. If you think about this, the molar mass of sodium chloride is about 58.4 grams per mole. So in 1 mole, you need 58.4 grams of sodium chloride. So if you have 1 mole per liter of sodium chloride, that's equivalent to having 58.4 grams of sodium chloride per liter. That's quite a lot. Often we're dealing with things that are a lot more dilute. So for dilute solutions, we'll often avoid using molarity and we'll use other units. So one of the common units that are used for dilute solutions are what are referred to as parts per million. You might have heard that. Sometimes that's expressed in terms of, it's called ppm. And what this means is that we have milligrams of solute per kilogram of solution. Okay, milligrams of solute per kilogram of solution. So if I write something as having 400 ppm of carbon dioxide, what that means is that I've got 400 milligrams of carbon dioxide for every 1 kilogram of solution. Okay, that's what that means. Why does it work out to be ppm? Because in 1 kilogram of something, there are a million milligrams, right? That's why. So you probably famously have heard that the concentration of carbon dioxide in the atmosphere has been, for the first time in a very long time, consistently exceeding 400 parts per million. So this is the carbon dioxide concentration across a whole year. You can see it kind of dips around a little bit. It's going from 400 down to about 390. That's due to the fact that plants don't grow very much in the winter, so it kind of tends to die off in the winter and then come back in the spring. So so you know that's what that's all about. And so we see this kind of, I mean, it's just a little change across the whole year, isn't it, right? But generally, it's around this 400 ppm part that's a convenient unit for measuring something like carbon dioxide in the atmosphere. Moles per liter would be just kind of like, would give you kind of numbers that are hard to work with. Here's a sample of boron. It says 1000 ppm standard solution, so that just means we get 1000 milligrams of boron for every 1 kilogram of that solution, right? That's how we interpret that. If you've got a really dilute solution, then sometimes we'll work in what's called micrograms of solute per kilogram of solution. Because there are 1 billion micrograms in a kilogram, we'll call this parts per billion, or ppb. So when I read this and it says 500 ppb copper 2+, what does that mean? It means that there are 500 micrograms of copper 2+ for every 1 kilogram of the solution. Okay, so that's for super dilute stuff. Often things that are like very very active. Often sometimes things like hormones are active at parts per billion levels, and that it's worth noting that. So we've got molarity being the most common unit of concentration that we'll use in chemistry. Then for more dilute solutions, we have ppm, and then for even more dilute solutions, we might use ppb. Now, a lot of people, particularly those that are working in medical science, will often express concentration in terms of a percentage. And there's a couple of ways that they'll do this. One is percent by mass, and the other is percent by volume. And you do want to be really clear what you mean. So we indicate percent by mass by writing the percent symbol, and then we put mass over mass, and you'll see where that kind of notation comes from in a moment. And if we mean percent by volume, or what's often referred to as volume percent, we'll put the percent symbol and then we'll follow that up with volume on volume, just to make things super clear. Percent by mass and percent by volume will be different for a given solution. Almost always they are different. So percent by mass is pretty easy to calculate. You do the mass of the solute divided by the mass of the solution, and you've got to multiply it by 100. Now notice here it says mass of solution, so we do need to be mindful that the solution is composed of both the solute and the solvent, and we need to add together both parts to get that. So simple problems would just be calculating what is the percent mass of a solution given appropriate information. So we can go ahead and do one of those now. So it says, what is the percent by mass of a solution composed of 7.6 grams of sucrose dissolved in 83.4 grams of water? Remember our formula for percent mass on mass. It is mass of solute, and the solute is the minor component, over the mass of the solution, which is the sum of both components, the solvent and the solute, and then you've got to times that by 100. So the mass of the solute in this case, sucrose is the smaller component, water is the larger component, so sucrose is the solute, that's 7.6 grams. And then the solution is composed of both components, so 7.6 plus 83.4 grams, and then finally got to times that by 100, and that gives us 8.4. And see how we correctly gave it units, percent, and we put it as mass on mass, because you can see that we did two masses on top of each other, right? Mass on mass. That makes it super clear. Okay, a more complicated problem is similar to that molarity problem that we did before, where we were asked to calculate the mass of the solute to produce a particular concentration of solution. So this question asks, what mass of potassium chloride must be added to 125 grams of water to produce a 15% mass on mass solution? So we're going to begin with our formula for percent mass on mass. It is mass of the solute, which is KCl, divided by the mass of the solution, which is the sum of the mass of both of the components. The solvent in this case is water, and the solute is KCl. And then you've got to times that by 100. So that's a lot to write out. We're trying to solve for the mass of KCl, so I'm just going to let that guy be X. So our percent mass on mass is 15. Then our mass of KCl is X. Our mass of water is 125. And our mass of KCl is X, and that's times 100. So I've just got to kind of solve for X now, and I'm done. So my first step is I'm going to divide both sides by 100. And that gets me to there. And then I've got to sort of distribute everything and solve for X. So I'm going to multiply both sides by 125 plus X, which I've done in this step here. And then now I distribute everything here. 15 on 100, by the way, is where I'm getting that 0.15 from. So I distribute everything and on the left-hand side, and I get that term. And then now I just got to kind of collect all the x's together, which is what I've done here. So I subtracted away the 0.15x from both sides, and that leaves me with that term. And then finally, I divided both sides by 0.85, and I get my answer for what x is. So now what I always like to do is to go back in and put it into the formula and check that I got things correct. So percent mass on mass is going to be my mass of solute over the mass of the solution, and we got to times that by 100. So the mass of solute, according to this, was 22.1 grams of the KCl, and then my solution is 125 plus 22.1 grams, and then I got to times that by 100 and put that all into my calculator. Sure enough, I'm going to get 15. So 22.1 divided by 125 plus 22.1 times 100, and it ended up being like 15.1. So it was correct with the we rounded for significant figures. It's totally fine. All right, so yeah, that works great. Okay, so oh yes, it looks great. 15.02 was the unrounded value. We're going to round that to 3 sig figs, and it ends up being 15.0% mass on mass. Perfect. Okay, so we haven't talked about percent by volume. We should do that now. Percent by volume is calculated similarly to percent by mass. It's the volume of solute over the volume of solution. So we'll just do a quick example calculation here. Remember that we indicate percent by volume as being percent volume on volume. So it says, what is the percent by volume of 125 mils of an aqueous solution? So that's my volume of solution. That contains 47 milliliters of ethyl alcohol. Ethyl alcohol is the stuff that gets you drunk. And so that's going to be my solute. It's the smaller component. So it's volume of solute over volume of solution times by 100. And it ends up being about 37.6% volume on volume, which is typical for alcoholic spirits, right? So vodka, brandy, whiskey, bourbon, things like that. Often, you know, they'll have a alcohol concentration of around about this number, sometimes a little more, generally no less than this. Okay, so I mentioned that people that are working in the medical sciences often love percent concentrations, and one of the reasons is because they make sort of dosing calculations kind of intuitive in a sense, more so than perhaps molarity. So percent concentrations are often used as conversion factors between amount of solute and volume of solution. So if a nurse or a doctor was to see something labeled as 15% mass on mass, one way that they might interpret that is that it contains 15 grams of the solute for every 100 grams of solution. So I pretty much, if I want to give somebody 30 grams of solute, whatever that might be, I immediately know that I'm going to need to give them 200 grams of solution. So that's kind of why those guys like these types of things. But what's important to recognize is that you can interpret this when you're doing these dosing calculations as two conversion factors, right? The same goes for volume to volume percentages. If it's 6% volume to volume, how do we interpret that? That means you get 6 mils of solute for every 100 mils of solution. And of course, you can write that as two conversion factors, which allow you to convert between mils of solution and mils of solute. So they can be really kind of useful for doing those very simple, very quick dosing calculations. Okay, so that concludes this section on solution concentration. We looked at three sort of classes of solution concentrations. We looked at molarity. We explained that molarity is the measure of solution concentration most commonly used by chemists. We then looked at ppm and ppb, which are often used when we're talking about dilute solutions. ppm refers to milligrams of solute per kilogram of solvent, while ppb refers to micrograms of solute per kilogram of solvent. And then finally, we looked at percent concentrations, and we explained that there can be either percent by mass or percent by volume, and we need to be very clear in our labeling of percent concentrations to indicate that clearly. We explained that percent concentrations are often favored by people that are interested in doing dosing calculations because of the way that we can interpret those concentrations very simply. Okay, I hope you found that helpful. Like I said, this last section is mostly quantitative, so make sure you practice and give plenty of numerical examples when you're getting ready for your tests and exams and so forth. Okay, good luck with everything. Bye.